So thanks a lot. It's going to be a pretty hard act to follow all the talks of today. I was very impressed by everything. And from two very impressive theoretical talks, I'm going to go back to practice. And from a Viennese accent, I'm going to challenge you to figure out which Austrian accent I have. The ones that know where I'm from are excluded, of course. So I'm going to talk about low-rank tensor approximations for sampling high-dimensional distributions. And I should first of all acknowledge Sergey, because this is mainly Sergey's work, who is a world expert on low-rank tensor approximations, and my two statistics colleagues, Colin Fox and Karim Anaya. So I'm going to try to stick with what the initial entry talk was about, telling us to try to speak to the other community, possibly boring my community a bit, but I hope I will say something to both. So the scene has been set quite well. I've got a physical process which is described by a PDE, typically. I will certainly look at that for a first example. I've got parameters, boundary conditions, and geometry which might be unknown or uncertain. I'm going to use data in order to try to calibrate those parameters and the other things that are unknown. And I do this via the data, describing the data via some functionals of the solution, or modeling the link between functionals of the solution and the data. And then there is going to be inference on the parameters, for example, in the clear inverse problem, or some quantities of interest that might be inaccessible. And the example that has been shown before and that I'm going to use throughout, at least for the first part of the talk, will be again a diffusion type equation which models subsurface flow. And that's parameterized, as was nicely explained by Chris, by a set of parameters. And I'm also going to stick with uniform or transformed uniform parameters as well, bounded. So I've got a set of d parameters, theta 1 to theta d, but I've also got an x, a spatial variable. So this is a continuous problem in some function space. And I'm going to have to deal with discretizing both with respect to x, because I can't solve this PDE explicitly, and in some sense discretizing or dealing with the parameters. So because typically in these applications like subsurface flow, the uncertainties are complex, you need to expand, as it was described in the previous talk, especially to regularize in a very high-dimensional parameter space, and a naive approximation would obviously, in a tensor product grid, would obviously be unfeasible. N to the d is just unfeasible. So a lot of my talk, I've kind of put primers everywhere, that I want to highlight that I'm not going to be exponential in d, I'm going to be linear in d. And everything is paying attention to being linear in d rather than exponential in d. So in the inverse case, which is obviously the focus of this whole workshop, we have given data and this PDE, and then we want to say something about kappa, the parameter function, or about some other quantity of interest. So this is even more difficult in high D, because as a deterministic problem, it's an ill-posed inverse problem to say something, knowing something about u, say something about kappa. And then there is, of course, intrinsic stochastic uncertainties as well. So I'm going to treat this in the Bayesian formalism, and so I'm going to follow on pretty much on what we've heard in the previous talks. So in the Bayesian formalism, we think of our PDE solution u. Here I've just dropped the x dependence as a function of the parameters. We are observing some functional of this, so this would be our observation operator O, that typically maps this functional valued thing into something that we actually can observe. We can't observe a whole function. We can only observe some finite number of things. And this could be point evaluations or averages, as I'm going to use. And I'm going to assume this sort of additive Gaussian noise model to model the measurement error. As Chris was saying, for this talk, please, I'm not going to model discrepancy, or I'm not going to talk about model discrepancy. The PDE is the truth. And the data would be then a vector y star of values that we have measured, and that is entering this modeled for the data. So now consider all this as probability distributions, and then we're talking about prior density on the parameters before we're using any data. We're talking about likelihood, which is given a parameter value, what's the likelihood to observe y star? So that would be the distance from of the observation operator with the data, knowing the noise, in this case IID noise. And then the Bayes theorem tells us that a posterior distribution, so the parameter given data, can then be expressed via this formula. And we are interested, as I said, in some quantity of interest, which is itself also then a random variable q of theta. So the ultimate task in this example, this q could be, for example, one or two of the parameters that I might want to infer on, or it could be some other functional. But the final objective will be to calculate these integrals that we've seen in Chris's talk already as well. So here we have the integral with respect to likelihood and prior, and then the normalizing constant. Okay, so what are typical approaches? And I'm sorry if I'm not got your approach that you would use, but if I want to work this integral out. So given this unnormalized density pi here, okay, and given some quantity of interest that I might want to infer something on, in particular, I'm going to be always thinking about things that are non-smooth. So for example, this probability of the event that theta 2 is bigger than theta 1. Then what could I do? I could stick a set of quasi-Monte Carlo points on there, and I could count how many fall in the white region, how many fall in the gray region. But obviously, with respect to this density pi, there is a lot of waste, a lot of points that are not really useful. And especially if this posterior or this density concentrates extremely strongly, then you will very soon get very slow convergence. If you did a direct quadrant on a tensor grid, okay, in 2D this might still be sensible, but in higher D, we know that this grows like n to the d. I've already told you this. And in particular, since we have a lack of smoothness of Q, we can't use many of these sort of advanced techniques that have been discussed a lot in this program already, like stochastic collocation or polynomial chaos, because Q is not smooth, and also the curse of dimensionality. I could do sparse grids. Again, similar thing. It's a bit better in terms of storage and curse of dimensionality, but if I have no smoothness, then this is not going to work. One of the workhorses in statistics, of course, is Markov chain Monte Carlo or random walk Markov chain Monte Carlo, and you see there's the burn-in, so it'll take a while until it walks in here. There is many rejections, which costs you effort. There may be long correlation times in the chain. As you see, the step size is fairly small here. And there might be poor mixing. I've only just started to kind of get up there into the gray region. So what can I do to improve this? And what I'm going to talk about for the rest of this talk is I'm going to build a surrogate pi tilde of pi, and then I'm going to use what statisticians have been suggesting for years. You can use MCMC with this as a proposal. You can use importance sampling, etc., in order to use this. So the important bit is I can try to convince you that there are cheap surrogates available via low-rank tensor decomposition that allow us to get such a nice spread of points in the density cheaply. So what is a low-rank tensor decomposition? It's essentially a separation of variables. So you say I'm approximating my tensor, which in principle has n to the d entries, so I'm now discretizing on a grid with n points in each direction. So from now on you can think of the discrete version of this whole thing. But from practical point of view, I'm approximating this tensor here by a sum of products of univariate tensors. And so I'm basically taking these small blocks here which are not which only have much lower rank. In fact, they all rank 3 tensors, and therefore I can construct these tensors. I can do integrals with this. I can do samples from this, all in order d times n cost. So linear in d. Okay, so I'm going to give you the take-home message now, so in case you fall asleep or it gets a bit too tight, too intense, you have at least learned something. So I'm going to tell you in a bit that we can construct and store this, and we only need a number of PDE solves that's linear in d. I have a tunable approximation error, epsilon, by adapting the ranks in my low-rank approximation. So I can make this cost and storage polylogarithmic in this tolerance or in this error. It's generic, so it's a black box thing. You basically give it to the toolbox, and it will calculate it for you. And for a lot of people from the statistics community here, I know are doing experimental design or design rules, and this is essentially sequential design, and this is the main thing I'm going to tell you about, why this is a good way of building it, because it does 1D slices. So to be precise, for those that do know anything about tensor approximation, I'm using about cross algorithms for tensor approximation, and it uses 1D slices, and that's why I call it a sequential design, because we're adaptively going to find those. As I said, it's going to end up as a product form, and therefore I can cheaply integrate, because it's just integrate with each individual univariate function. So it's univariate integrals. And I can do, and this is the main heart of the talk, I can do sampling from it via the conditional distribution method. Some people might know it as the Rosenblatt transform. Both of these linear in D. And then there's many known ways, and I'll give you 3 examples of how to use this in a sampling from the actual pi, not from pi tilde. So let me start with 2D, and let me give you the basic idea. So it is a low-rank approximation. Many of you have probably come across this, of a two-variate function here, and I'm going to call the error by cutting this expansion off at rank r with epsilon. So I'm going to show, or I'm going to assume that the rank is small, and in many problems where there's smoothness in structure, this will be the case. Therefore, the cost in storage will be reduced from from n squared to 2nr. SVD, or principal component analysis, as people know, it provides, in some sense, the optimal approximation with rank r in this sort of notion here, in the Frobenius norm. But it requires me to know the whole matrix here. It requires me to have all entries in order to build it. I want a method that does not require this, because once I go to d dimensions, then I have n to the d points, which I don't want to all evaluate. So this is where the cross algorithm comes in. This is a bit dark over here. But in essence, it's using interpolation arguments to argue or to show that if you pick the right index sets, I and j, both of size r, so essentially the right rows and columns in my matrix, then the matrix that is formed by this low rank approximation here is a good approximation for P. So this is basically related to, I was going to get no, it's on the next slide. This is related to, if you think about LU factorization, you're doing it in a block way. If you find the block of indices that has the largest value as a sort of determinant of that block, then you essentially have already captured the majority of your LU factorization, and the remainder that you're going to factorize afterwards, if you've continued and finished the LU factorization, will be small. And there is, in fact, this theoretical result that if you did find the optimal one that has the largest determinant, then you'd be off by r plus 1, factor r plus 1 from the best low rank rank r approximation in these norms. Okay, this is the maximum absolute entry. This is the standard 2 norm. But how do you find good sets in practice? So we don't want to solve this NP-hard problem, and how do we do this in higher D? Okay, so this is where I was going to use the board, so maybe I'll use this one because there's a bit of light here. Just to give you the basic idea, I'm not going to get the full TT approximation, you all to understand that. But I want to at least get the design, the sequential design method across. So basically what do I do in 2D is I'm going to pick a bunch of random columns of my matrix. So let's say I'll pick those 3. Okay? And I'm evaluating, as I've sort of indicated with these lines, I'm evaluating the tensor or the matrix at all those entries. Then I'm going to work out for this submatrix the best I values at which the determinant of the subblock that I'm getting, this 3 by 3 subblock, is maximized across all possible 3 by 3 blocks that I can pull out of this. And then I continue. So now I have my, I use these and I do my, I evaluate along those yellow lines, and I do again find the max wall, and this might now be these guys, and I iterate, okay? And this process converges rather fast, and it converges to a fairly good low rank approximation with controllable error as I go on, okay? There is obviously bells and whistles. I'm not going to do this P inverse here really in reality. I'm going to do a QR factorization and not an LU factorization, and I'm going to do a rank revealing QR, and then I can do rank adaptation. I can expand and I can grow and shrink my rank as I wish, as the data or the solution tells me. There's similar algorithms, several that exist. So this is the adaptive cross approximation by Bebendorf. It also has a lot of familiarity to the discrete empirical interpolation method by I don't want to pronounce that name, and Sorensen. But the important bit is how does this extend to higher dimensions? And in higher dimensions, I think you had some of you who were here had a talk in the last workshop by Lars Grasedik, where he described a more general framework. I'm going to look at one of the simplest tensor representations, low-rank tensor representations, which is called the tensor-train. It comes from physics. You see here the old references, and it basically, because I should say that while there's a unique way of doing a low-rank matrix approximation, there's no unique way of doing it in tensors. It depends in which way you're grouping the variables. So here we have essentially what we're going to do, and this is going to be even shorter than my little intro on cross algorithms for matrices. I'm going to give you an even shorter intro on cross algorithms for tensors. You use in particular, okay, I should maybe finish with this slide before I do the cross. So the representation is essentially, here is a rank 2 tensor, which links the first variable with the remainings. Then the next is essentially a rank 3 tensor, which links with the first variable, has the whole range of the second variable, and then links via alpha 2 with the third and so on variable, etc. So they are all little rank 3 tensors. So these sort of little cubes with small r's and big N. Okay, long, thin cubes. So first of all, these we're assuming that the ranks are all bounded from above by R. This is going to be one of the things that we're always going to have later on. And as you can see already just from drawing this picture, the storage will be D order dnr squared. Linear in D again. Okay? So here is the algorithm, and I really don't think it's easy to take this in, but so let's think of our tensor in 3D. Okay? So here's your 3D tensor. Here's my variable 1, here's my variable 2, and here's my variable 3. So essentially what you do is you matrize, it's called, or you unfold the matrix, the tensor, and you essentially make it into a thin matrix. And now I can do the same algorithm. Okay? So now I'm going to take, for example, 3 here, and I'm going to pick the largest values from the determinant again, and then these 3 will be my next set I1. Okay? Now I don't go straight back because I have 3 variables. I go on to unfold alpha 1 with I2 versus I3. Okay? And you basically do this forwards and backwards. This is what this algorithm here should say. So essentially I'm going forwards through starting with random initial sets of columns that I'm evaluating, going forward all the way to D, to k equals D, and then I'm going backwards and I'm changing my j's. So first I've built i's, which are already informed from my Max-Wohl algorithm, and the j's are untouched. And then when I go back, I'm going to improve the j's for the fixed i's, and I go forward and backward. So you see that the number of samples now is going to be dnr squared, because for each individual ik here, I need to take r up to r values from here and up to r values from here. So that's r squared values for each. And for each of those r squared values, I'm evaluating along the whole line. Okay? So this is the important bit. I'm exploring, and this is why I think this is a very sophisticated way of exploring in high dimensions a function, because it explores in a whole range of one unit variable and then uses some linear algebra in order to choose adaptively where the next lines in the other directions are supposed to be laid. Okay? And again, everything here is linear in D. So what do I do for the inverse problem? So again, in the workshop 3, and I know that many of you were not there was a talk by Sergey describing how we're using this algorithm I just described to do an approximation, a surrogate of the whole PDE solution U. So I'm going to build a surrogate of U tilde by combining this TT cross algorithm I just described with a model order reduction approach, and we get a TT approximation of U tilde, and hence also any functional I want from U tilde in TT approximation, or cheaply. And now the important bit is when I'm going to do my TT approximation of pi, so rather than what I just described, I'm not going to use pi itself. I'm going to use inside my likelihood function. Remember, my pi has a likelihood function that depends on the observation or model response O of U. And I'm going to use U tilde there. So that makes it cheap. I don't have to evaluate any more extra functions, any PDE solutions, to build my pi. And if the q theta, the functional I want to do inference on, is also smooth, then I can build a TT for that too, and I can integrate. And this can be done in linear in D. So I've got everything univariate in the parameters. But if q theta is not smooth, or if you don't know whether it's smooth, you can use a sampling-based quadrature. You can use quasi-Monte Carlo methods, you can use Metropolis Hastings, etc., and this is what I'm going to come to next. So how do we actually sample efficiently from these TT surrogates? So I know, so far I've only shown you that it can be written as this product of these tensors, but I haven't shown you how I would do sort of the inverse. How do I sample from that? And then how would I use it to sample from the original posterior? So here is where the Rosenblatt transform comes in, or the conditional distribution method. We can write always the density, in most cases, the density as a product of conditional densities. So pi 1, sum pi 1 of theta 1 times pi 2 of theta 2 given theta 1, etc., etc., etc. And so if this was cheap, then this would be a nice way of univariate distributions, but the individual conditionals are, of course, integrals again. And again, in order to do this, I could just first of all work out the integral, integrate this out, and then do a 1D CDF inversion. So for the rest of this talk, I'm not going to describe at all how I'm doing the 1D CDF inversion. I'm assuming, and there is a lot of literature on how this can be done efficiently. So in a 1D function, there's no problem in doing an inverse CDF inversion. But I have to do this integral. And equally, to get the kth step, once I've already fixed my first k-1 samples of the ith sample, the first k-1 components of the ith sample, to get the kth one, I still have to integrate out the remaining d minus k. And so the problem is that I have a d minus k dimensional integral in each step. For the TT, of course, and you see where I'm going, this is not the case because I have the product form. And so I can just do this again in the same way as I did the TT iteration to build my tensor. I can work my way forward and backward. In the one direction, I'm doing these univariate integrals and then combine these matrices together. Once I've integrated the middle variable out, these are now matrices in alpha d and alpha d minus 1, etc. So I can just multiply all this out. Equally on the front, where I've already sampled, I can multiply them out. And I just get a univariate CDF inversion again for this one thing here. So the cost per sample is d order d Rn, again linear in d. So the problem now is, of course, that we're sampling, in this case, from pi tilde, and that I have an error. So I could, first of all, just build a biased estimator via Monte Carlo quadrature with respect to pi tilde, or I could even use QMC seeds. And you see they're now very nicely sitting inside there already, and I get very good accuracy, but I'll get a biased estimator. Or I can use these samples that I can draw, IID samples that I can draw from this distribution via this conditional distribution method as proposals in Metropolis Hastings, and I reject them with this acceptance probability. Or I can use them as a control variate. So I use QMC as I've just described on the previous slide for the control variate, and then I only do the estimate of the difference. And that has obviously much lower variance if this is, these two densities are very close. So that would require less points. And the best, actually, as you will see on the next slides, is importance sampling. I just integrate with respect to pi tilde. So now we are actually very close to what Chris showed you. So instead of doing a ratio estimator with respect to the prior, I'm essentially suggesting a ratio estimator with respect to pi tilde. And I'm actually suggesting the same thing, to use QMC. So here is the problem. Again, also very similarly, the only difference being that I'm doing a log uniform. So the log of kappa is described in the way Chris had it. In fact, I've even got very similar phi k functions which decay in norm with a certain power of nu. And my thetas are uniform random variables. Here I've chosen d equals 11 and nu equals 2. And I'm discretizing on a grid with 1/64. The spatial discretization error I'm not playing around with. I've got pressure averaged over these squares here as my synthetic data for some synthetic theta star. So I'm doing a mathematical problem in some sense, not a real problem. And I've added noise variance 0.01 in the plot I'm showing you. We've also done 0.001, and it works well as well. And I'm using flux through this cell, or the average flux, and the probability that the flux exceeds 1.5 as our functionals. So here is just to show you how the acceptance rate, or 1 minus the acceptance rate, the integrated autocorrelation time, and the error all converge extremely nicely with respect to delta, which is the accuracy in my TT approximation, and with respect to n, which is the number of points I'm taking in each variable. And I'm going to show you the three methods. So TTMH stands for Metropolis Hastings, CVQ stands for control variate, and ISQ stands for importance sampling against two methods. So this is the ratio estimator that Chris had in his talk, and this is the DRAM, which is being proposed by these Finnish colleagues. And all the random, the QMC rules are randomized rank 1 lattice rules, so they're unbiased estimators. And so here is the final slide. For n equals 32 and delta equals 0.1, you see that here is DRAM. Here, blue is the Metropolis Hastings. You see it's slightly slower convergence. All the QMC-based methods are converging slightly faster, and the importance sampling method is by far the best, because it really exploits the QMC points here. And even more so in the case of an exceedance probability where we really outperforming everything else quite far. And if you look at, this is the line where the discretization error would lie, and you actually compare how much cost it would be to reach that line with your method, you see how much we are outperforming the other methods, the competitors. Just as a final thing, this is not restricted to PDE-constrained inverse problems. You can build also TT approximations of these Weibull models or distributions with hyperparameters here. So this is an example from this paper, which is a shock absorber data set with partially censored data, and where we're doing the posterior 95% quantile to show that we can do complicated quantities of interest as well. And again, against DRAM, we are by far outperforming it in terms of CPU time. Here we're talking about factor almost 100 improvement. And one last thing, maybe, there is obviously a setup cost, and you would probably have asked this question. And this is obviously tunable by what n and delta you choose. But it is in the same ballpark as the burn-in that you'd have with the Metropolis Hastings for this example. So just to put the take-home message up again, I've already said all of it. I don't need to say it again, because I said it earlier. Important bit is linear in D, and it's black box. So, and you can tune how accurate you want it, which might be important if you're not planning to use it within Metropolis Hastings as an important sampling technique. Thanks.
So TT toolbox is a pure linear algebra algorithm. How to guarantee that P tilde, so surrogate, is positive and also integral is 1?
Yeah. So that our integral is 1 doesn't matter because we're working all our algorithms we've used were working with unnormalized densities. But that it's positive is important, and we're basically taking the absolute value. So what that does, because all our algorithms that I've described were sampling based, it just means that I'm losing a bit of efficiency. I might put some point somewhere where I've made a negative value positive, but it doesn't have any effect on the it's correct.
But did you say that it's not important that it integrates to 1? I thought you're using inverse TDF methods.
Inverse TD.
For sampling from that pi tilde, aren't you?
No, I'm doing only these univariate ones. And for those I can integrate out I can find the normalizing constant. I'm never doing the inverse for the combined one.
Yeah, but the individual ones, they have to integrate to 1, right?
Yeah, but as I've shown in all my algorithms, I'm calculating the normalizing constant as well. So I don't need to be normalized.
So if the parameters are on an unbounded domain, say with Gaussian measure, is the proposal that you get from doing the TT approximation of the forward model, can you say anything about its tails and whether that, whether it becomes because it could become a bad biasing distribution, for instance, if the tails.
I haven't looked at that, but I mean we just put a bounding box in that case, and yeah, no, I haven't. We haven't looked at that. Be interesting to talk.
So, how robust are these methods to, there are certain things, like for example, I thought your important sampling results were very impressive, because my experience is important sampling works well if I get the importance right.
Yeah.
When I don't.
That's right.
Also, are there internal checks and consistencies that were shown me when I've oversimplified or overassumed?
Yeah, this is the nice thing. I think this is the nice self-tuning nature of it. So if you look at this plot here, these things, the delta is really what you put in, and the n is what you put in. And the epsilon here, the brown line, is the actual error that we have checked against a detailed calculation. So you see that these things are actually very predictive. And they really tell you how good the approximation is.
So when you say against the detail calculation, does that mean you have to make the detail calculation?
No, this was just for this curve, not in the actual calculation. You don't need to do this detailed calculation because I'm showing you that this is very much giving you the correct.
But were you to not be doing the correct because of in fact it didn't.
Well, it's the ranks. It's the ranks where you'd see it. It's in the ranks. The ranks would grow up, and the efficiency would basically get worse. Yeah, that's where you see it.
Okay. Oh, sorry. We'll take one more question. Pardon me.
So you're using a surrogate model for the sampling, but is it anything special about using TT?
No.
You could use the surrogate model, right?
And this is what I've said the last 2 weeks to my statistics colleagues. I think you can leave it to anybody in the room that's a mathematician to give you a surrogate that can be used, that is good for high dimensions, that is good for dealing with various properties, it's cheap to get. And then I was trying to advocate some ways of how to use that afterwards in a clean Bayesian inference.
Because then you might get rid even of the linearity in the dimension. You can get log terms.
That's right. So yeah, I mean, if the dimension is not that high, you might want to use stochastic collocation or something and say, I accept a little bit of growth, but any surrogate. So I'm just saying there is many algorithms out there that can clean up after the numerical analysts.
We'll take one more question, then we'll
Yeah,
head to coffee.
so these rank counts, they are linear in the number of parameters, but they are somehow polynomial in the rank of these core tensors. Yeah, these little.
Yeah, that's right.
Long. And this is cubic or quadratic or cubic or something.
The flops is cubic, yeah. The flops is cubic. Yeah.
In these pictures here, what are the R? Because you have fixed the R somehow, or is the R?
No, in this case the R changes as it goes down, as it gets more accurate. In this one it's the N we're changing. In this one we're changing the delta.
Right. So, but then the rank is depending on the epsilon or the.
That's right.
How did you choose it?
It's adaptive. In this particular implementation of the cross algorithm, the Sege has this Amen algorithm, which is can adapt the rank. It can increase the rank. It can reduce the rank.
So this was done with this Amen module. Then you don't have a. Okay, so then the ranks are produced by the Amen, yeah. So it could.
So this is empirical. There's no proofs. I'm not claiming any proofs. I'm just saying empirically. This is what you observe, and the ranks are, the ranks are essentially just indirectly visible here, because I'm not cheating with the CPU time. The CPU time is what it is. If the ranks were high, then you wouldn't see these.
So one more night, Robert, and all the speakers for a great afternoon. Thank you.